Okay, so thank you for staying on to this lecture, and I hope that today we will have a broader exposure to Dirac notation, and this will help you, in understanding the use of Dirac notation, especially how we can express quantum gates in matrix form and how we can express them in the Dirac notation, or sometime that's called, the operator form. Uh, Even though essentially we can say the matrix is operator and it's operator in the other way as well, but most of the time when we work with more involved operators, it's usually more helpful to work in Dirac's notation than with matrices, because when you increase number of qubits, if you keep writing in matrix form, we have seen that for single qubit we need a matrix of size 2 by 2. For 2 qubit gates, we need a matrix of size 4 by 4. And similarly, if we keep going for 3 qubit system, we will need matrices of size 8 by 8. So the matrices are scaling to power number of qubits. So that's actually one reason that since the matrices are scaling exponentially in the size of the system, if we have to simulate, let's say, a quantum system, or if we want to simulate quantum computer itself, we will need exponentially, many resources than qubits. For example, for a 100 qubit quantum computer, if you want to simulate it on a classical computer, you need matrices of the size 2 power 100, which are huge. So that's why it's not easy to simulate quantum system on a classical system, and it's sufficient to simulate them on quantum computer. So anyway, so this argument aside, you see that working with matrices is, exponentially more difficult. So that's why we are emphasizing on learning Dirac notation, because that's helpful for working with larger number of qubits. So even though, it's not apparent when we are working with 1 or 2 qubits, because then the amount of work almost seems to be the same either in matrix form or Dirac notation form. But as the number of qubits increase, working with matrices becomes almost impractical. Okay, so that's why today I will, sort of review some concepts from previous lectures about Dirac notation and build upon them, and will introduce more examples of single qubit and 2 qubit gates. And I will also actually correct one thing that I made an error in the last lecture when we were talking about 2 qubit gates. So hopefully today we will have a better picture of how to handle 2 qubit gates. So for that, let me start sharing my OneNote. And thank you very much for suggesting to use this OneNote for Windows, because this is better than the Windows journal that I was using. Anyway, so let's begin today's lecture. And today our focus is going to be on 1 and 2 qubit states and gates. And we will try to explain Dirac notation in more detail so that you become comfortable with this thing. Now, before I go to Dirac notation, I want to actually take an example of real plane again. So a real plane is a very simple system that most of you are hopefully familiar. So it has an x-axis and a y-axis. So if we have some vector A, we can represent this vector in component form using, let's say, unit vector I and unit vector j. That if I have this vector A, I can find its projection or component along x-axis by taking its dot product with I and writing it I, plus I can find its projection onto y-axis, which is a dot j, and write it along with j. So that's my j component. Usually a dot I is written as ax and a dot j is written as ay. So this is how we write these vectors in component forms. And just to prepare an analogy with the notation, with the terms in Dirac notation, this pair of vectors ij, this is called the basis. And this has these properties that if you take the dot product of I with itself, it's 1. If you take dot product of j with itself, it's 1. And if you take dot product of I with j, it is 0. Or if you take dot product of j with I, it is 0. So it's an orthonormal set, that the vectors in the basis, they have all magnitude 1, and they are orthogonal to each other. In general, our basis doesn't have to be orthogonal. I mean, all it really needs is to be linearly independent. But most of the time we work with the orthonormal basis anyway. Okay, so this is basis. And as you can see, we can actually very easily construct another basis. For example, you can have some vector I prime and some unit vector j prime. All you need are just, them to be orthogonal or at least linear independent. And then you can prepare projections along these I and j vectors and then express your vector in terms of these new unit vectors as well. It's like equivalent to rotating your xy plane and then expressing all of your vectors in terms of new ij. So that can work. So that's why we can have multiple bases for the same plane. Similarly, and when we talk about Dirac notation, if I talk about a two-level system, which is a qubit, it means that we have two states, let's say these, and we can represent one state with the symbol 1 and the other state with symbol 0. Now, a general quantum mechanical state is given by this, that it can be in a superposition state. Now we can think about, we can represent these basis states in matrix notation as well. And in that case, this 1, let's say we represent it in 0, 1. That's usually the convention, but we can do it other way around as well. So this is 1, 0. And we can see that this pair of vectors 0 and 1, they satisfy like similar properties as your I and j vector, that the inner product of 0 with 0 is 1, and inner product of 1 with 1 is 1, and inner product of 0 with 1 is 0, and inner product of 1 with 0 is 0. So they're orthonormal. So it means we can use these two vectors to represent any state psi in terms of 0 and 1, where this A and B are nothing but the projection or component of state psi along 0 and along B. For example, this A is essentially this scalar that you project this state to 0, and this B is this scalar that you project or find inner product of your state psi along 1. So that's why you can write this state psi like this as well. That's how most people would write, but this is just a scalar. You can write it on left side as well, or left side, right side of this 0 and 1. So and this is this is just the same as when we talk about vectors in a 2D plane, because this is your sort of x component, this is sort of your y component. Now, since in a real plane, we can find the magnitude of a vector, magnitude of vector by finding the square root of the dot product of A with itself. Similarly, we can find the magnitude of this vector psi, and this is, represented many ways by different people. For example, you can write it like this. So this is dot product of psi with itself, or there could be other symbols as well. And this, in this case, would be just the square root of A mod square plus B mod square, because this psi bra is nothing but the complex conjugate transpose of this state psi. So you take conjugate and you can take transpose. So this A becomes A star since it's a scalar, so no worry about transposing. And this 0 column vector now goes to the row vector, and we represent it with this 0 bra 0, and then this B becomes B star, and like this. And now I can take this inner product of psi with psi like this. A star 0 plus B star 1, A0 plus B1. Now, orthonormality will be very useful whenever we are working with, evaluating inner products, because this 0 inner product with 0 would be 1. So I'm left with A star into A, which is A mod square. This 0 inner product with 1 will give me 0 because they are orthogonal. So the cross term goes away. Similarly, 1 into 0 is 0. And this 1 into 1 will be 1. And I'm left with B mod square. And we can find its magnitude by taking its square root. And now I can prepare a normalized state vector psi as 1 over A mod square B mod square square root A0 plus B1. You can similarly normalize, any bra vector as well. You can find its magnitude by finding its corresponding ket vector and then taking an inner product with that and dividing by the square root of the inner product. Okay, any questions so far? Perfect. Now, before we move on, let me emphasize that just like a real plane, we can rotate our system and have another pair of unit vectors and express the components of vectors with respect to those unit vectors. Similarly, we can construct other orthonormal bases for this two-level system as well. For example, one famous basis is the basis of this plus minus vector, where plus is defined as this 0 plus 1 and minus is defined as this 1 over 2 square root 0 minus 1. And you can verify yourself that this plus into plus is 1 and this minus into minus is 1 and plus into minus is 0 and minus into plus is 0 as well. So they also form an orthonormal basis, and any vector psi can also be expressed as some linear combination of these states. Okay, and we can easily find these A prime, B prime. For example, if you know that psi is A0 plus B1 and you want to find out what are A prime and B prime, all you need to do is put the value of plus and minus in terms of 0 and 1 and then collect the coefficient of 0 and 1 state. For example, this plus is 1 over square root 2, 0 plus 1. This minus is 1 over square root 2, 0 minus 1. So if I, by the way, let me make it full screen. Okay, that's good. And now this psi is, let's collect this coefficient of 0. So this is A, this is not prime. This is just A over, no, sorry, this is prime. Yes, this is prime. A prime over under root 2 plus B prime over under root 2 is coefficient of 0, and a prime over under root 2 minus b prime over under root 2 is the coefficient of 1. Now, I know that this is equal to a, so I have a prime over under root 2 plus b prime over under root 2 as a, and I have b equal to a prime under root 2 minus b prime under root 2. Now you see these are two simultaneous equations. A and b are known, but a prime, b prime are not known. You can solve these two equations and you will have the value of a prime and value of b prime known to you. And then essentially you have been able to express your state psi as a function of plus and minus state. So we can equivalently, express our states in terms of any basis, and we can go from one basis to another basis in the same way. Okay. Now, let's see how we can represent single qubit gates. Single qubit gate. Suppose I have some gate G, which is acting on some qubit Q0 and transforming it into Q0 prime. Now, this Q0, if you think about in matrix terms, this is some general column vector A and B. Okay, and if you think in terms of Dirac notation, you can write this Q0 state as some okay, you can write it as A0 plus B1. So you can either think in terms of the matrix column vector, or you can think in terms of the Dirac notation as a state vector. Now, let's say if it is, you think about this K0, the state as a column vector. So after this operation, this single qubit, first of all, is still single qubit. Its state is changed. So it means AB, after this gate, is transformed to some other state, A prime, B prime. And this matrix has to be a 2 by 2 matrix. This, if you think about this single qubit gate as a matrix, it has to be a 2 by 2 matrix, because a 2 by 1 column vector is being transformed to another 2 by 1 vector column vector. So the only possible transformation is a 2 by 2 matrix. So let's call it some G11, G12, G21, G22. So this gate G is, can be specified like this. And really speaking, you can do all of the quantum computing analysis, algorithm building using these matrices. You don't have to go to Dirac notation. The only trouble is this, that as the number of qubits increases, the size of this matrix increases exponentially. So it becomes extremely hard. So that's why working with the Dirac notation, is much easier. And I think it also has to do perhaps with this habit of humans that have been developed over several centuries, that we have developed this habit, at least most of the people, if you don't consider some Far East Asian nation where people write vertically, but most people now write on paper, horizontally. So Dirac notation also provide a way to, keep writing horizontally. Anyway, so we can think about these matrix operation in terms of this 2 by 2 matrix, or we can think about it in terms of Dirac notation. And for that, the tool that has been developed is this outer product form. And for that, let's see what this outer product is. So if and I'm now going to relate the outer product with the matrix notation. So this 0 is a vector, a state vector, or a state ket, sorry. So it has this symbol 1, 0. It has this notation 1, 0. And this other 0 on the right is a state bra. So it is the conjugate transpose of this, and its conjugate transpose is this 1, 0. So now if I carry out this matrix multiplication, this 1 into 1 is 1, 1 into 0 is 0, 0 into 1 is 0, and 0 into 0 is 0. So it means if I have a matrix like this, I can replace it with something like this. Similarly, if I take an outer product of 0 with 1, so 0 is 1, 0, and 1 is 0, 1. So 1 into 0 is 0, 1 into 1 is 1, 0, 0. So if I have a 2 by 2 matrix like this, I can replace it with an outer product like this. So similarly, if I have 1 into 0, you can check that this is equal to 0, 1, 0 matrix. And 1 into 1 is 0, 0, 0, 1. Now, since we have a 2 by 2 matrix, which can only have at most 4 components, and our basis has, 2 vectors. So all possible, the possible, order products can only be 4, and we have all 4 of them here, 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 and here. Now let's see this, general gate G, and I can now write it as G11 1000 plus G12 0100 plus G21 0010 plus G22 0001. Now you see, I already know what's the representation of this matrix, what is this, this, and this. So I can quickly write it G11, and this is nothing but 0, 0 in outer product form. G12 0, 1, and G21 1, 0, and G22 1, 1. So this is, I mean, at least operationally speaking, this is how I can convert a matrix operator to the outer product form. And actually, from now on, you can do it directly. All you have to do is remember that this term corresponds to 0, 0. This term corresponds to 0, 1. This term corresponds to 1, 0. And this term corresponds to 1, 1. So after doing all of this, from now on, you can quickly write these operators. For example, the X gate is 1, 0, 0, minus 1. And since this 1 corresponds to this 0, 0, and these two are 0, so only minus 1 is, which is 1, 1. Now, this, Dirac notation have an other advantage as well. And that is actually much more, I would say, useful advantage than just this operational, nicety that instead of writing bigger matrices, we can just, write these things in rows. And that is that in, matrix form, for example, I want to see what X gate does to state 0. And from this thing, I see that this 0, 0 minus 1, 1, when it is applied to 0, I know that orthonormality exists. So when this 1 inner products with 0, this term will be 0. And when this 0 inner products with 0, I will get 0. And similarly, if I want to see that what's the action of X gate on 1, I can check like
I think the Z gate.
Sorry?
Because I think Z gate, the X gate is 0, 1, 1, 0, right?
Oh, yes, you're absolutely right. My apologies. Let's say, thank you very much. This is actually the Z gate that I was talking about. So Z gate doesn't do anything to 0 state. And when it is applied to 1, so this 1 into 1 is 1. And this 1 into 0 is 0. So I'm left with this thing. So now this I have, worked out. But now once you develop this practice, all you can do is if you want to see what Z gate does, you don't even have to do all of these things. You just go to this definition and you see that since this one state is written here, when the 1 would be operating from the right, this will giving a non-zero value only with this term, and I will be getting -1. Since it's a 0 here, when this 1 would come to 0, this is gone. So I can see immediately from here that one state goes to -1 and 0 state goes to 0. Okay, so this is an advantage that you are able to quickly see the action of the gates on individual states of the qubit. Similarly, let's now talk about the X gate, which is actually 0, 1, 1, 0. And since this term 1 comes at the place of 0, 1, and this one is at the place of 1, 0, now I can quickly see that when X applies to 0, 0, 1 plus 1, 0 coming to 0. Now this 0 into 0 is 1, and I'm left with this 1, and this 1 into 0 is 0. So X on 0 is 1, and I hope that you can now quickly see that when X is applied to 1, I get 0. And this thing is already encoded, in this form. It's a bit harder to see actually this thing from matrix notation, and it's easier to see from Dirac notation that 0 is going to 1 and 1 is going to 0. And actually, if you write its truth table in such a way that you write output on the left side and input on the left or right side, that an X gate by definition transforms 0 to 1 and transform 1 to 0, you can actually convert this truth table directly to this operator form, that you write the 0 on right and 1 on left, 0 on right and 1 in left, except that you have to change this cat to bra, and 1 on right and 0 on left. Okay, so let me, since we are doing these things, introduce a couple of more single qubit gate. The other one is the Hadamard. We have actually already talked about it. So Hadamard is this H is equal to 1 over square root to 1, 1, 1 minus 1. And I hope that you can now appreciate quickly that I can write it as 0, 0. So this one is in the place of 0, 1. This one is in the place of 1, 0, and this minus 1 is in the place of 1. Now, first of all, you see quickly what is happening. That this tells me quickly that if I apply this Hadamard to 0 state, so there's a 0 on the right here and the 0 on the right here. So this is 1, this is 1. So when 0 will come from the right side, this term will not contribute, this will not contribute. Only this and this will contribute. So I will get 0 plus 1. Similarly, when H is applied to one state, this will not contribute, this will not contribute. I will get only 0 minus 1. And since these states come again and again, we have a special name for this. We call this plus state and we call this minus state. Okay, so let me introduce one other gate. It's called phase gate. And it has this symbol S. And its definition 1, 0, 0 iota. Some people actually write it 1, 0, 0 exponential iota pi by 2, because exponential iota pi by 2 is actually iota. Now I want to write it in the Dirac notation, and you can quickly see that this is 1, so 0, 0, and this is iota is in the place of 1. So I can write it exponential iota pi by 2. Now you can see what this gate does. This gate transform the input 0 to just 0. But if the input is 1, it gives it a phase pi by 2 because it multiplies it with iota. So this is the truth table of this gate. And if you're given the truth table, you can directly write the Dirac operator form for this gate, because 0, 0, 0, 0, 1 exponential iota pi by 2, 1, 1 exponential iota pi by 2, 1. Okay, this is this actually sometimes is also called a rotation gate around z-axis that gives a rotation of pi by 4, and we'll see shortly later why. So any question so far? Good. So since we are talking about these 1-qubit gates in detail, let me introduce a couple of other gates which are actually very important. These are the actually since all gates are rotation gates anyway, even though some people call these rotation gates, but since all gates actually are they are rotation gates in essence, because they don't change change the magnitude of the state, they only change different weights. So but to separate them from other places, I would like to call them arbitrary rotation gates, because our X gate was 180-degree rotation around X axis, our Z gate was 180-degree rotation around Z axis, our Y gate was 180-degree rotation on Y axis. So they were fixed rotation. But we can also have arbitrary rotation gates. For example, Rx gate, which is the arbitrary rotation by angle theta around X axis. And by the way, this is available in Qiskit as well. You can specify arbitrary value of theta and rotate your state. So this has this matrix form: cos theta by 2 minus iota, sine theta by 2 minus iota, sine theta by 2, and cos theta by 2. Now, this form actually is easier to write if you are familiar with the quantum mechanics, where we generate these rotations by exponentiating different operators. For example, we don't have to worry for this course, but this comes from minus iota theta by 2 into x, where x is sort of a generator of these rotations, where this theta by 2 specifying the angle. But anyway, without worrying these things, you can just remember that this is a gate for arbitrary rotation around x-axis by theta. Similarly, we can have a gate for rotation around y-axis by some angle theta, and this is given by cos theta by 2 minus sine theta by 2 sine theta by 2 cos theta by 2. And similarly, this comes from exponential minus iota theta by 2 into y, exponentiating the y gate. Similarly, the rotation around z axis is exponential minus iota theta by 2, 0 exponential iota theta by 2. So this is this rotation around z axis, and since I can write it by taking this minus iota theta by 2 common, putting 1 here, 0 here, 0, and this becomes exponential iota theta. And you see that this rotation around z axis is essentially this matrix 1, 0, 0 exponential iota theta with this global phase exponential minus iota theta by 2. So that's why this S gate, which was written 1, 0, 0 exponential iota pi by 2, is basically a pi by 4 rotation around z axis, because if I take exponential iota pi by 4 common, it will develop this form with the theta is equal to with theta given by pi by 2. So this is actually a pi by 2 rotation gate. So you take exponential minus iota pi by 4 common, and this becomes pi by 4. This becomes exponential iota minus iota pi by 4. And if you compare it with this thing, then theta will have to be pi by 2. So this is a pi by 2 rotation around z axis. Okay, and if you want to, let's say, write this gate in Dirac notation, it's very easy. I hope now that this Rz can be written as exponential minus iota theta by 2, 0, 0, plus exponential iota theta by 2, 1, 1. So it's giving this one state exponential iota theta by 2 phase, and 0 state exponential minus iota theta by 2 phase. Sorry, can you please speak a bit loudly? I'm just barely able to make it.
जो आपने ऊपर नीचे करके कमेंट दिया है e raised to power minus iota theta by 2, अगर आप इसको साइन में हमें चाहिए था अर्थ फोर्स में, तो iota theta के ऊपर
Sorry, come again.
तो आप मेरा माइनस साइन कॉमन दिया है ना, तो इधर नीचे इसका साइन चेंज नहीं होगा, e raised to minus iota theta.
No, so I can write this exponential iota theta by 2 as exponential iota theta minus iota theta by 2, because when I take theta by 2, subtract theta by 2 from theta, it becomes theta by 2. So that's why I can take, and this is exponential minus iota theta by 2 anyway. So 1 here and exponential iota theta here. Okay. Good. So this is a pi by 2 rotation gate up to, you know, this global phase exponential minus iota theta by 2. Okay, so any question about single qubit states and gates and how to express them in Dirac notation?
Sir, ये RZ को S गेट बनाने के लिए pi by 2 का एंगल लेंगे हम?
Yes.
All right.
You can see it from here as well. So this is now written in the form that 1 is here. So if theta is pi by 2, this is essentially this gate except with this global phase exponential minus iota theta by 2. So these rotation gates are actually going to be important later on in our algorithm development. All right, so let's now, you know, come to the 2 qubit states and gates, and hopefully that we will be able to remove confusions today. So first of all, these 2 qubit states are states of 2 qubits. Let's say you have qubit A and qubit B, and our fourth postulate of quantum mechanics tells us how to construct states of you know, multiple quantum system. And for that, let's say I want to write the states of this A and B system. So to build the sort of the basis state, we can start from here by assuming that this is in 0 state, qubit A, and this qubit B is also in 0 state. So the symbol actually is this 0 sub A, 0 sub B, but since we can always remember that what A, B, this first qubit refers to A and the second qubit refers to B and so on. So I can forget this subscript A, B, but sometime we can bring them back if there is any confusion or we need to keep track of different qubits. And similarly, some people don't write this, you know, tensor product and this 0, 0 is written, and some people are even lazier and they just write it 0, 0. But this is essentially a state which says that qubit A is in 0 state and qubit B is in 0 state. Now let's develop the matrix notation for this state. So this 0, 0 state is 1, 0 tensor 1, 0, which means that this 1 first multiplies with both of them and I get 1 into 0, and then this 0 multiplies with both of them and I get 0, 0. So this 1, 0, 0 column now column vector now represents this 0, 0 state. Similarly, I can find out the column vector representation for 0, 1 state, which is 1, 0 tensor with 0, 1, and this is 1 multiplies with 0, 1, I get 0, 1, 0 multiplies with 0, 1, I get 0, 0. So 0, 1 is this 0, 1, 0, 0 vector. Similarly, 1, 0 is 0, 0, 1, 0, and 1, 1 is 1, 0, 0, 0, 1. Now, we can easily check that these 4 states now 0, 1, 1, 0, 0, 0, and 1, 1, they form a basis, because we can see that 0, 0 into 0, 1 is 0. Because let's check this. For example, this is 0, 0 state. So this 0, 0, when I will make its bra, it will become 1, 0, 0, 0. And this 0, 1 is over here. So this is 0, 1, 0, 0. And let's take their matrix product. So 1 into 0 is 0. 0 into 1 is 0, 0 into 0 is 0, plus 0 equal to 0. So we see that this inner product is 0. Similarly, you can check the inner product of any two states, any two different states, and you will see that they are 0. Plus, since only one is coming, when we will take inner product with themselves, this will give us 1. So we have this thing that 0, 0 inner product with 0, 0 is 1. 0, 1 inner product with 0, 1 is 1, and so on. So in general, we can easily see that the x sub I, x sub j, this is equal to 0 if your ij are different, where I'm labeling such that I'm calling this as 1 state. Let's call this 0 state, let's call this 1 state, let's call this 2 state, and let's call this 3 state, just for indexing purpose. So if I and j is not equal to each other, the inner product of these states is 0. And if they are equal, the inner product is 1. This, by the way, sometimes also written as delta ij. So this delta ij symbol is 0 when I and j are different, and when this delta ij symbol is 1 when I and j are 1. Where I have defined, x0 as 0, 0, x1 is 0, 1, and so on. x2 is 1, 0, and x3 is 1, 1. So now we have a basis to deal with 2-qubit system, and that is this, this basis. Now let's see, can we write any general state in terms of these basis states or not? So for that, let's say the most general state of 2-qubit system can be A, B, C, D, right? So it's a 4x1 column vector. So we can have A, B, C, D in general. And I can express this column vector as A 1, 0, 0, B 0, 1, 0, 0, C 0, 0, 1, 0, plus D 0, 0, 0, 1. Now in operator form, this 1, 0, 0 is 0, 0. This 0, 1, 0 is 0, 1. This 0, 0, 1, 0 is 1, 0, and this 0, 0, 1 is 1, 1. So it means, first of all, that I can express any state psi in Dirac notation using these, basis state. Where if we want to find out what A is, so A is nothing but the projection of psi on 0, 0 state. B is nothing but projection of psi on 0, 1 state, and so on. So these are, you can think of it, as a 4-dimensional plane, and these as your unit vectors. I don't know, maybe x, y, z, w unit vectors, and then this is x component, y component, z component, and w component, and so on. Okay, so let's now get to 2-qubit gates. Since a general 2-qubit state is a 4x1 column vector, it means if we think in terms of matrix, then that matrix has to be a 4x4 matrix. Let's say if this is some gate G, it has to G11, G12, G13, G14, G21, and so on, up to G44. So our general 2-qubit gate is given by this 4x4 matrix. And let's now, think about how we can construct these gates in matrix form and in Dirac notation form, because this is going to be the key for algorithm development and analysis. So let's first talk about states. 2-qubit states. Okay, and we can think about, two types of states. I have 2 qubits, and one types of states are which are independent states. Independent states that you can express the joint state of the system as some state of qubit A and some state of qubit B. But there could be combined states or entangled states or correlated states of these, two qubits, such that the state cannot be written as product of qubit A state and qubit B state. However, they can still be written as, some superposition of the basis state, where there is some sum over ij. And these basis states psi psi j are those states 0, 0, 0, 1, 1, 0, 1, 1. And these are some, coefficients. So there are some states which can be written as product of some two states, and there are some states which cannot be written as product, but they can be written as, in terms of the basis, as a superposition of those basis states. And these states that that are independent, they're called unentangled state if the system is a pure quantum mechanical system, and they are entangled state if it's a pure quantum mechanical system. So in this course, we're not talking about, mixed systems where can be mixed states, because then correlation may not always mean entanglement, but let's not worry about that. Okay, let me give some examples. So for example, this is an unentangled state. Another example is a state like this, right? Because I can write it as 1 over square root 2, 0 plus 1 tensor 1. I can take this 1 on the right common. So this one, so now it's a product of this and this. So this is still unentangled state. But let's take another example. Suppose this. And we saw a circuit to prepare this state. This I cannot write, product of two individual states. So this is, the entangled state. All right. So we saw a circuit to prepare, such Bell states yesterday. Similarly, let's talk about two types of 2 qubit gates. So 2 qubit gates, because they can be of two types as well. Independent gates, that there are, let's say, 2 qubits Q0, Q1, and some gate A is acting here and some gate B is acting over the second qubit. But there could be some gates that are dependent, or that they are being applied on both at the same time, or they are conditioned or controlled gate. For example, the most common example is these controlled operation, but they can not it's not only controlled. There are swap operations that you swap 2 qubits, or there are other operations that are they're not just controlled operation that you do something on one with respect to the other and so on. But in general, these are operations that happen on 2 qubits together. So they have this, gate representation, something like this. That I can't write it as a factor like this. An example is, a control X gate, or a control Z gate, or a swap gate, and so on. Now, when we have independent gates, then the combined gate can be written as a matrix product of the individual gates. For example, if this is an X gate and this is a Y gate, then I can, for X gate, I can write 0, 1, 1, 0. For Y gate, it's 0 minus iota, iota 0. So their total matrix is this 0 into all 4. So this is 0, 0. This 1 into all 4, 0 minus iota, iota 0. This 1 into all 4, 0 minus iota, iota 0. This 0 into all 4. So this is how I can prepare the matrix for this combined gate. But when this is a giant operation, I cannot construct a gate through this tensor product form, as I did by mistake yesterday. That when we were talking about this controlled X gate, I said, okay, this is I gate, this is X gate, so we can write it IX, and I prepared a matrix from there. So that was wrong, because that we could do only if the situation was like this. So if you have a qubit, nothing happening to this qubit, and X gate always happening to the second qubit. So this is Q naught Q1. So it doesn't matter if the first qubit is 1 or 0, this X is always happening to this side. So in this case, you could write the combined gate. Sorry, this is. So in this case, you can write the combined gate as I tensor X. But when it is a controlled X operation, then I cannot get the matrix form from here. For that, I will have to go to the truth table. For example, for the C naught gate, the truth table is like this, that I want a system that transforms 0, 0 state. So this is input, output, 0, 0. So the first qubit is control, the second is target. So 0, 0 goes to 0, 0. 0, 1 should go to 0, 1. But 1, 0 should go to 1, 1, because no control is 1. So target should flip, and 1, 1 should go to 1, 0. Now this 0, 0, let me just write again, was 1, 0, 0, 0. So I want, a matrix that converts my 1, 0, 0 to 1, 0, 0. And this 0, 1 is 0, 1, 0, 0. So the same matrix should convert this 0, 1, 0, 0 to this. And this 1, 0 is 0, 0, 1, 0. So my matrix should convert it into 1, 1, 1, 0, 0, 1, and 0, 0, 0, 1, which is this 1, 1 state. This should be converted to 0, 0, 1, 0. Now I have to construct this matrix, and that matrix actually is this. That 1, 0, 0, 0, because when it acts on this 1, 0, 0 state, it should give me 1, 0, 0 back again. So there has to be, a 1 here. And when it acts on 0, 1, 0, 0, it should still give this thing. So there should be a 0, 1, 0, 0 here. But when it works on 0, 0, 1, 0, it should give me a 0, 0, 1. So there should be a 1 here. And when it acts on 0, 0, 1, 0, it should give me 0, 0, 1. So there should be a 1 here. And you can check that when the input is 0, 0, 1, 0, the output is going to 0, 0, 1, and so on. So this matrix, I will have to prepare it from definition. I cannot get it by tensor multiplying I and X. That's number one. Now the second part is, how do I get the Dirac notation for this two qubit gates? And for that, we will have to go back to the basis. So our basis was 0, 0, 0, 1, 1, 0, 1, 1, and check out their all possible combinations of outer products. And for that, let's begin from 0, 0, 0. So 0, 0 was 1, 0, 0, 0 into 1, 0, 0. And this is 1, 0, 0, 0, 0, 0, 0, 0. Similarly, you work out 0, 0 into 0, 1, and so on. And you will see that it has this notation that, G corresponds to like this, that this element is 0, 0, corresponds to this one. The next one corresponds to 0, 0, 0, 1. The next one corresponds to 0, 0, 1, 0. And the last one corresponds to 0, 0, 1, 1. And similarly, this one corresponds to 0, 1, 0, 0. This one corresponds to 0, 1, 0, 1. And you get the idea. So which means that if I look at this matrix G for my control NOT gate, I see that there is one at the 0, 0, 0, 0 location. There is one at the 0, 1, 1, 0, 1 location, and this one is at the 0, 1, 0, 1, 1, and this is the 1, 1, 1, 0 location. So it means the G for control X is 0, 0, 0, 0 plus 0, 1, 0, 1 plus 1, 0, 1, 1 plus 1, 1, 1, 0. And this is because this corresponds to the product of 0, 1, 1, 1, and this corresponds to product of 1, 1, 0, 1 states. Okay, any questions so far or any confusion?
Yes, sir.
Please go ahead.
Sir, एक तो आपसे पूछना था, what exactly is the controlled gate या swap gate, अगर intuitively समझना उसको.
So
And
it's
yes.
it's exactly what its name says. For example, you have 2 qubit, and you have first qubit that is acting as your control. So you ask if my control is 0 or not. If your control is 0, you don't do anything to the target qubit. But if your control is 1, that is giving you a command to do the gate on the second qubit. So if it is a controlled X, you do the X on the second qubit. So if the second qubit is in 0 state, it becomes 1. If it is 1, it becomes 0. I mean, X gate is applied to the second qubit. Okay.
Okay, sir. एक और चीज पूछनी थी. Sir, 2 qubit gates से ऊपर जो examples दी हुई हैं, उसमें जैसे example 2 है, जिसके अंदर दिया है 1 by √2, 0, 1 plus 1, 1 वाला. तो इसके बाद टेंसर प्रोडक्ट की फॉर्म में लिख दिया, तो इसका मतलब है this is an independent state.
Yeah, the states of 2 qubits are independent of each other.
Okay. ठीक है sir. Yes, sir.
So it doesn't matter that you have written it like 0, 1 plus 1, 1. That doesn't tell us if it is entangled or not, because that is just a way of writing. We know that the 0, 1 really means 0 tensor 1, and this 1, 1 really mean 1 tensor 1. And I can take this 1 common from the right side. So the right qubit is in 1 state, but the left qubit is in this superposition state. But that is its own state. It has nothing to do with the state of the second qubit. But I cannot do this factorization for this state. So that's why this is entangled, that both qubits are in some joint state. Any other question from anybody else? If not, let me actually go to this point, which I think is sort of, at the heart of today's lecture, which is, can I write this Dirac notation representation of this gate intuitively and directly from the truth table? Because the truth table of this controlled X gate, by the way, sometime I was writing X, sometime I'm plus. So the official symbol for the control X gate is this plus. That this is Q0, Q1, and this means that if Q0, so let's write input on this side, and this is output Q0 prime, Q1 prime. So Q0, Q1 here, and output I'm writing now on the left side. So if Q0 is in 0 state, then doesn't matter what Q1 is, the state remains the same, because the control is 0, so the target is not changing. But if the control is 1, the target flips. So target goes from 0 to 1 or 1 to 0. So that's why it's controlled NOT gate. And if you see at the Dirac notation, you see that's what this Dirac notation is telling us already, because this is 0, 0. It means if I take a product of this gate with a 0, 0 state from right, this 0, 0 because of orthonormality, is going to give 0 here, going to give 0 here, going to give 0 here, and it's going to give 1 here, and I'm getting 0, 0 output. So that's why, sorry, this first one is 0, 0. So the 0, 0 is being transformed to 0, 0. So that's what this first term is telling us, that 0, 0 state goes to 0, 0. Now for the 0, 1 state, we see that the 0, 1 state similarly is being transformed to 0, 1 state. Similarly, this 1, 0 state is being transformed to 1, 1. And this 1, 1 state is being transformed to 1, 0 state. So that's why the Dirac notation is, much more intuitive and tells us about the gate right away. And you can write it from the truth table in a much easier fashion than writing it from the matrix form. Okay, so does everybody get this idea?
Yes, sir.
Perfect. So let me take, a couple of other examples. For example, if I have this controlled Z gate, let's see, can we now write its Dirac operator form, its operator form in Dirac notation directly. Control Z gate, first of all, is this thing, that it doesn't do anything to 1, and it gives a phase to input 1. So if this is Z, so now a controlled Z gate officially should do this, that if your input Q0, Q1, I'm writing input on the right and the output on the left side. So if the control is 0, 0, it doesn't matter if your Q1, if your target bit is 0 or 1, you get the same state. But if your control is set to 1, you have to apply Z gate to the second qubit. So it means this 0 will still come out as it is, because that's what Z gate does, but this 1 will get a minus sign. So it means I can write its operator form now directly. 0, 0 goes to 0, 0. So 0, 0 goes to 0, 0. 0, 1 goes to 0, 1. And 1, 0 goes to 1, 0, but 1, 1 goes to 1, 1 with a minus sign. So this is how I can write the, control Z operator form directly. So in the, in today's activity, you will be asked to have, this control S gate and write its operator form, and you just construct its truth table, and from the truth table, you can write the operator form directly. Okay, any question about this thing again? If not, I want to take the next, 10 to 15 minutes to introduce a really, useful idea, which is very important when we start thinking about the hardware. So the idea is this, that your quantum computer hardware usually only provides a few gates that can be done with the small error, and that is, dependent on the type of hardware you choose. For example, if you are working with superconducting quantum computer, it has, a certain set of gates which it can do efficiently in smaller time and with less error than other gates. Similarly, if you're using a trapped ion-based quantum computer, it can do some other gates more efficiently than perhaps the gates that are being done by superconducting quantum computer. And similarly, if you're working with a photonic-based quantum computer or other types of hardware structure, they may implement some other types of quantum gates. So it's always, a struggle that when you are working at a higher level, for example, in Qiskit, you are just thinking about the algorithm and the gates, and you're not thinking if this gate is being implemented directly in the hardware, or hardware has to use some assembly language to convert my gate into those gates that it can, implement more efficiently. And for this practice, let's, talk about this thing. For example, if you talk about controlled operations, there are several controlled operations that you can think of. For example, control X, control Z, control S, controlled arbitrary rotation. For example, you want to have a gate that does a controlled rotation around y-axis by 30 degrees. That's what you want in your algorithm. But your quantum hardware may not actually implement controlled rotation at all. It perhaps can only implement controlled Z, or it can only implement controlled X. So the assembly language will have to convert this higher level gate to a gate to a set of gates that can work to give you this gate. And one of the most common technique actually is this. For example, in superconducting quantum computers, you can implement control X very efficiently, but you are not allowed to implement other control operation. For example, control Z is not allowed, control arbitrary rotations. They will not allowed mean that they will take much more hardware time. So people have developed ways of implementing a set of gates with controlled X, and that's what I'm going to talk about right now. For example, you want to implement a controlled Y rotation. So let's think about this block sphere again. This is X-axis, this is Y-axis, this is Z-axis, and you want to rotate your state. Let's say it is along the Z-axis, but you want to rotate within the XZ plane around Y-axis by 30 degrees. But you want to do it conditioned on this qubit Q0, that you want to implement this controlled operation. So the usual hardware for this thing is this, that if you want to implement a controlled rotation by an angle theta, what you do is something like this. You do a rotation. Let's say, okay, this is RY I'm talking about, let's say control RY. So you do rotation around Y by theta by 2, half of theta. And this you can do, okay, this is only a single qubit rotation. This is not a controlled qubit rotation, but then you do a controlled X operation, and then you do a Y rotation with respect by minus theta by 2, and then you do a controlled X again. And this whole gate actually give you a controlled Y rotation by theta. And let's see how. So when you do a rotation, if your controlled qubit, this Q0 is 0, what will happen? If this is 0, this X will not happen and this X will not happen. And you can see this is already identity, because you first rotate by theta by 2 and then you rotate by minus theta by 2, you will get identity, and that's what should happen. It doesn't matter what is state here, what is Q1. If Q0 is 0, you will always get Q1 again at the output. But let's see what happens if Q0 is 1 and not 0. If it is 1, you first do rotation by theta by 2. So you wanted to rotate by 30 degrees. So what you do, you only rotate by 15 degrees, and then you apply control X. What control X does? Control X rotate your state around X-axis by 90 degrees. So from here, you rotate around this cone, which is making this external angle 15 degrees. So your state come from here to here. So now this is angle 15 degree with the negative Z-axis over here. And what you do a rotation by minus theta by 2 around Y-axis now. So this is Y-axis. So minus theta by 2 mean that instead of rotating clockwise, you rotate anti-clockwise. So your state goes from this 15 degree to 30 degree because you rotated in the opposite direction. And then you apply X gate again. So when you apply X gate again, you rotate back in this plane where you were already, but now your external angle is 30 degree and you get to, a 30 degree rotation. So the net result is that if the Q0 was 1, you got a rotation of 30 degree around Y-axis. So basically it's like this. You do a half rotation, then you flip, you do half rotation in the opposite direction, which is, equal to the total, which is equivalent to adding of the two rotation, and then you rotate back into the original plane, and you are able to implement the controlled rotation. But you only use CX, and you didn't use a new gate CRY. Okay,
सर सर ये अगर आर वाई जो रोटेशन है जो सेकंड वाली है -θ/2, अगर सर ये पॉजिटिव θ/2 होती तो तब तो सर कुछ फर्क ना पड़ता ना?
बिल्कुल एग्जैक्टली, आपने बिल्कुल सही कहा है, क्योंकि वो जब हमने एक्स किया था तो हमने डायरेक्शन फ्लिप कर दी थी, तो अगर पहले θ/2 रोटेट किया फिर थीटा, तो वो बेसिकली व्हेन वी आर हियर ऑन दिस साइड, अगर यहाँ से आप वापस θ/2 करते हैं, व्हिच इज मीन दैट you are rotating, this is y axis, you are rotating, this is the positive direction and this is the negative. So पहले मैंने यूं किया, लेकिन फिर फ्लिप किया, अगर फिर मैं वो क्लॉकवाइज ही करूंगा तो I will actually be going in this direction, and वो जो 15 डिग्री था वो वापस 0 पे चला जाएगा, and when I flip back from here I go to this axis.
तो सर ये सारे गेट्स के लिए होती है बात ट्रू है या फिर कोई स्पेसिफिक गेट्स ही हैं?
For rotation around z and y axis, you can do it exactly like this, because z and y are orthogonal to x axis. और मैंने आपको होमवर्क में ये प्रॉब्लम दिया है कि think about a way of arbitrary controlled rotation around x axis using cx. So you'll have to think a little bit and come up with a strategy that how can you implement controlled arbitrary rotation around x axis but use only cx. Okay,
जी ठीक है सर.
thank you. Any question about Dirac notation and these two qubit gates or these things? If not, let's take 10-minute break, and we will back for a small lecture and a lab session on teleportation.